Remember, we are having the test on Friday, and so as you know, I'll remind y'all again on Wednesday, but most of you know this, that we'll have it in this room. I'll get the test out at 7:15. All right. You may come at 7:15. You're not required to, but you should be able to work through the test in an hour, but that extra 15 minutes. And you'll have assigned seating, so there'll be a seating chart up front. You'll have 15-inch multiple choice, 4 to 6 free response, and it will cover chapter 0 and chapter 1. Just those two chapters. We might get to the next chapter, which is on 0.5. There will be a derivation that you'll need to do beforehand. I'm not sure which derivation it'll be. It might be one of the ones that's in your book, or it might be one that I'll give you. I'll send an email out about that today, but it'll be worth 10 points. It'll be like what you've done before. So those of you that are new, we're going to do a couple variations today. It'll be similar to those. And you can find them on the internet. You can use any resources you want, but I do want you to write a paragraph describing just the steps that you go through. Okay? It should be an easy 10-point story. Is that clear? All right. Well, we're going to do a couple of those derivations today for calculating the electric field due to a line of charge or an object of charge, and we will either use integration or use the binomial theorem to figure out what is the electric field due to either a dipole, which we'll look at, which is a pretty common thing that occurs in nature, a dipole where you have two equal and opposite charges, or a continuous line of charge. We'll look at a ring of charge. I think a ring. Yeah, a ring, and then also a charged disk, which is where you allow the ring to be your differential element. I'll probably let y'all do that for your derivation, but don't run off and do it now. It might be this year. I'll have to think about it and see what either one you can do. Alrighty. You have any questions about the tests or what to expect this week? Life, whatever. No? Was there any big news from the weekend? Y'all go to parades? Was it fun? It was sort of fun. Yeah. Okay. Let's see. So most of the time, our electric field will be due to a regularly shaped charged object like a sphere, a ring, or a rod. Or even if it's not due to some regular object, you'll be able to approximate it to that object. So something that is approximately like a line or approximately like a flat sheet of charge. And so it's useful to have expressions for those electric fields of those objects. And so today we'll look at a couple of things. The first one is just a ring. Now a ring is very simple, especially if I'm looking at the electric field due to the ring at the very center of that ring. And we've done this before, but if we want to find the electric field of this ring at the center of the ring, then we break it into differential elements. So we'll break the ring into differential elements. And we'll call these differential elements, because they have a certain Q, we'll call them dq. Right, y'all are in integral, most of you are in integral calculus this semester, so you should be doing this. And then our next step is to add up the contribution of each differential element, dq, to the electric field. And we'll call each of these contributions, each dq causes a certain electric field. We'll call these contributions dE. So for example, if I think about these differential elements, this differential element up here, which is dq, it causes an electric field down here that is dE. So I just imagine this is a point charge. At this point, the electric field is in the direction of the force that a positive test charge would feel here. A positive test charge due to this charge plus dq would feel a force in the downward direction, so the electric field is also in the downward direction. Similarly, if I have this dq, my electric field, oh, I'm sorry, right? will be in this direction, opposite that. This dq will be in this direction. This dq will be in this direction. And you get the idea. You go all the way around the ring, calculating what is the contribution of each differential element q, dq, we're calling it, a little bitty, infinitesimally small portion of the charge on the ring. And we go all the way around, starting at one point and going all the way around to the other point, and we find the total electric field. Now we could write this as the electric field is equal to the integral of dE, but we know from our definition of the electric field that this is equal to E equal KQ over R squared. Remember, this comes about from, you don't need to write this down, but this comes about from our definition of the electric field, F over Q. That's KQQ over R squared over Q, and this is actually our test charge, and that cancels out. So that's how we can find that expression for the electric field. It just comes from Coulomb's law. You already have that introduction a day or two ago. So this is going to be equal to the integral of K dq over R squared. Now this is really simple. It's a very simple integral because the value dq doesn't depend upon R, because q is going to be the same distance for this particular configuration from the charge for every piece of dq. So it's a really simple integral because R doesn't depend upon q. dq doesn't depend upon R. I can just take that out of the integral, and it's going to be K over R squared integral of dq. Now, we'll go through some processes of doing that, but if I just look at the picture, what is the total electric field? If I take this and I integrate, or I add up all these pieces all the way around from one point to the next, what is going to be the net electric field as I go around this ring of charge? If I integrate over the entire ring of charge, adding up the electric field due to each little contribution, what is going to be the net electric field of this configuration at the center? It's going to be 0, right? Because if I go around and I go through this exercise of doing the electric field, I find that the electric field, that all those vectors are going to cancel out. So the net electric field at the center is equal to 0. So that's a really simple derivation for the electric field due to a ring of charge. At the center of a ring of charge, because of its symmetry and because of the way the vectors cancel out, the electric field is equal to 0. Well, let's look at some that aren't so simple. First, we need to just define a couple of terms. May I go down from here, y'all? It's a useful process. This is something you do in a lot of different areas where you're integrating over a particular object or integrating over a surface or a volume. All right. So when you're given distinct point charges like we've been doing, you just add up the electric field, you do the vector sum. We did an example of that where we had 2 charges, and we just take the vector sum of those 2 electric fields due to those 2 charges. But when you're given a continuous line of charge, you divide the object into differential elements. You know, that's our dq. And then we integrate over the entire object to find the total electric field. So we'll look at 3 configurations of charges. We'll look at the electric dipole. We're actually not going to do all 3 of these. We'll probably just do 2 of them, the first 2. The electric dipole, the charged ring. We just did the charged ring, but we'll look at the charged ring not at the center of the ring, but instead at a point up above the ring. And then your electric field is not 0 above the ring. And then also the charged disk. The charged disk is a lot like the charged ring, and you'll find either when you, charged disk, not ring. You'll find that when you do the derivation for the charged disk, that you'll use the results for the charged ring. Or you can, it's a lot easier. use the results for the charged ring, because you'll use the ring as your differential element and integrate over that ring. But again, that's probably what you'll have to do for your exam. You can find it online. I think, in fact, it's even in the homework. So if you look back at the homework videos, you can find it there. I'm pretty sure it is. So when discussing charged objects, too, we just need to make a few definitions about charge density. I think we might have done this last semester when we were doing moments of inertia, because this is a very similar thing to our moments of inertia. Remember, we had to integrate over objects to find the mr squared in order to derive the moments of inertia for different shapes, and we got that table with all the different expressions for moments of inertia. This is basically the same thing, except we just have a different equation that we're integrating over. We have kq over r squared instead of mr squared. So a couple different things we need to think about. The charge, we've already seen this. The symbol is q, and the units are coulombs. Then we also have some densities. The linear charge density, we usually call this lambda, and its units are coulombs per meter. It just says if I have a line of charge, how many coulombs per meter do I have? And then we also have surface charge density. We'll call this alpha, and this is coulombs per square meter. And then finally, volume charge density, and it's going to be kind of like mass density, rho, and this is going to be coulombs per cubic meter. So lambda, alpha, or no, not alpha, sigma. Lambda, sigma, and rho. Coulombs per meter, if I have a line of charge, how many charges per unit meter? If I have a surface area, like a flat surface, what is the charge per unit area, or coulombs per square meter? And then I have a three-dimensional object, how many charges per unit volume do we have? We'll use these to actually define the electric field. So I just want to define them right now. Okay, let's look at an electric dipole. We want to find the electric dipole at the point P, which is here, in terms of Q, D, and Z. So I have two equal but opposite charges, which is a pretty common configuration in, atoms and stuff, where I have one charge and another charge that are equal and opposite. And I want to know what is the electric field at some distance Z from the center, from a point that's equidistant between those two charges. So first, I just want to draw the electric fields. So if I think about this, the electric field due to this charge, it's going to be in this direction. And the electric field due to this charge down here is going to be in this direction. And actually, to draw them more to perspective, this electric field will be smaller because it's further away from that negative charge. Again, I've just imagined I have a positive particle here, ask myself what is the direction of the force due to these two particles, and that gives me the direction of the electric field. I'll call this one E plus, the red, and I'll call this one E minus, the electric field due to the positive and the negative charges. All right, so E total is going to be equal to E plus minus E minus. That's equal to KQ over R plus squared. R plus is going to be the distance from here to here. And then you can probably imagine that R minus will be this distance. Minus KQ over R minus squared. Notice that I haven't included the sign here. They're both equal but opposite charges, but I don't include a negative here to represent that this charge is negative. That's because that negative is already accounted for when I draw the vectors. All right, I want to express this in terms of Q, D, and Z. So I can rewrite this again. E is equal to KQ over Z minus 1/2 D squared minus KQ over Z plus 1/2 D squared. I'm just writing this r plus and this r minus in terms of z and d. So see, this is z, the distance from here to here, minus this distance. Or excuse me, z is this distance. Subtracting this distance gives me this distance. That's all I'm doing there. And for this one, I'm saying z plus 1/2 d gives me the distance to the negative charge. You could stop there. I mean, that technically is the answer in terms of q, d, and z. But we can simplify it a bit. And this comes up a lot. You'll probably see the binomial theorem in PChem, I suspect. You ever use binomial theorem? No? Okay, well, it can help us to simplify the expression quite a bit. I'm going to factor out a 1 over z squared from the denominator. So for example, where I have this 1 over z minus 1/2 d squared, this becomes now 1 over z squared times 1 plus d over 2z squared. I factored out a z squared out of this whole thing, and so I get this expression right here. You don't see that right away, that's not a big deal. But that's what I've done there, is I've just factored out a z squared from that denominator. And I can also make an approximation that when z is much, much greater than d, that's also saying that d over 2z is much, much less than 1. If z is a lot bigger than d, then d over z is a lot less than 1. If that is true, then I can use the binomial theorem. And this is the binomial theorem. It says that 1 plus x to the n is equal to 1 plus nx over 1 factorial plus n minus 1x cubed over 2 factorial. Of course, a factorial is just 3 factorial is 3 times 2 times 1. Okay? We're just going to use the first two terms of this. We'll just use these two terms, the 1 plus nx over 1 factorial, and we're going to let x equal d over 2z. And when I get that, my expression up here now becomes something that looks like this. It becomes E equals kq over z squared times 1 minus negative 2 d over 2z minus 1 plus negative 2 d over 2z. Taking this expression, factoring out the z squared here, applying the binomial theorem, letting x equal d over 2z, and it gets us to this here. Don't sweat too much sort of the details of this, but I do just want you to be aware that often people use the binomial theorem to take an expression and just make it a lot simpler. And you'll probably see that if you haven't seen it yet in calculus. You'll probably see it in PChem or in some of your upper level engineering classes. So not too worried about the algebra of how all this happens right now, but just know that this binomial theorem can be used in this to take an expression that looks complicated and make it a lot simpler. If I do a couple steps of algebra, I get an expression for E, which looks like this, kqd over z cubed. And so that is the electric field due to a dipole, where Q is the charge, the magnitude of one of the charges, D is the separation, and then Z is the point, the distance above the midpoint between those two atoms. Okay? That's real exciting, I understand. And you're not really going to see the binomial theorem on your exam, but again, I just want you to see it because you'll probably see it again before you're out of undergrad, or if you go on to graduate school or whatever, you'll see it again. Just the use of the binomial theorem in this way. If you haven't seen it already, you probably should have seen it in calculus, right? Binomial theorem? Yeah, okay. Well, maybe you will soon. All right, let's do the ring. The ring is more like what we did with the moments of inertia last semester, and it's more like what you'll need to do for your derivation for the exam. So let's take a look at it. The charged ring. For your exam, by the way, I'll send you out a document. It'll look something like this. It'll have a picture, and it'll just say, derive the electric field for this configuration in terms of the variables. It'll look a lot like this. And then you'll write out that derivation and write a short summation of what you did. But here I want to find the electric field at point P. And I want to express it in terms of Q, which is the total charge on the ring, Z, which is the distance above the ring, and then R, which is the radius of the ring. Okay, first thing we want to do is we want to consider our differential element. I've already shaded it in right here. This is our differential element. And the charge on that element, dq, that's going to be the charge on this differential element, will be equal to lambda times ds. Remember, lambda, that's our linear charge density. It says how much charge per unit length, and then we're just multiplying that times ds, the length of your little segment. Then the electric field due to that differential element, I'll call it dE, will equal to k dq over r squared. Just beginning with our original thing, and that's going to be k lambda ds over r squared. Now, I want to get it in terms of z and big R. I don't want it in terms of little r. That's part of my request here. And so I can express r in terms of big Z and big R. How do I do that? I'm going to use the Pythagorean Theorem, right? So I know I have R. I want to express it in terms of C and R here. So I can say that R squared will equal to Z squared plus big R squared, where big R squared is the radius of our disk. All right. I can also show up here, if I think about the vectors, that I have x and y components. So imagine here, I have an electric field that's in this direction. It has an x component, and it has a y component. This is Ex, this is Ey. Over here, due to this differential element, I have an electric field in this direction. It has an x component, it has a y component, Ey. So my net electric field is going to be in which direction? The x, the y, or somewhere in between? It'll be only in the y direction, because all those x components, they're going to cancel out. As you integrate around that ring, that Ex will cancel out in every direction. So Ex cancels, and the only thing remaining is the electric field in the y direction. Now, the electric field in the y direction, let me write this down here. Only Ey remains. And the electric field in the y direction is going to equal to the magnitude of the electric field times the cosine of the angle theta. I know that's not usually the case, but because of the angle that we have, if you look at the triangles that are involved, you'll see that the y component of that vector is going to be times the cosine of that angle. We saw that, with the inclined plane last semester. Well, sometimes our x component isn't the sine of theta, and sometimes our y component isn't. Sometimes our y component is not the sine of the angle. Okay, so only Ey remains. We also want to, so what we're really trying to find now is dE cosine theta. This is what we want to know. And we don't want it in terms of theta. We want it in terms of Q, Z, and R. So we need to make some expression for theta. The cosine of theta, this is my angle theta. It's going to be adjacent over hypotenuse. So it's Z over R, little r, which is equal to Z over Z squared plus R squared to the 1/2. So now I can find the differential for my electric field. I'm going to call it dE perpendicular. That's really just saying I'm looking for dE cosine theta, because that's the only electric field that's left after I integrate all the way around. And it's going to look like this. Putting all this stuff together is going to be k lambda ds over z squared plus r squared. That's our dE times the cosine of theta, which is going to be z over z squared plus r squared to the 1/2. I can rewrite this k lambda ds z over here times z squared plus r squared to the 3/2. All right, and this is dE. Now I'm to a point where I want to actually integrate across this. I'm going to integrate across the entire circumference of this circle. So my electric field, well, now I want to ask myself, what can I take out of this interval? Which of these quantities depends on S? Is Z constant, or does it change as I move around the circle, as S changes? This is a constant value. K, of course, is always constant. Lambda, constant, or does it change as S changes as I move around the circle? That's a constant value as well, ds. And then Z, we already said is constant. R also is a constant value. So everything can come out of that interval except for the ds. Now we sort of set it up this way so that we can pull everything out of the interval because we're putting all the terms in terms of things that are constant. So this is going to be z k lambda over z squared plus r squared to the 3/2 times the integral of ds. Now the next step we want to ask is, what are the limits of integration? We go back to our picture. We're integrating over ds. So I'm going to start here and let ds run all the way around. What are my limits of integration then for ds? What does it start and where does it end? I'll give you a hint, it's going to start at 0. Well, where is it going to end? My value, my final value for s, as I go all the way around that circular ring. What is it? Close. It's not 2 pi. You're good. You're thinking polar coordinates, but we're not really using polar coordinates. What is it? Okay, yeah, it does come back to the same point. But if I start on a circle and I go all the way around, I come back to the same point. I use a circumference, right? So, actually. No, okay. Yeah, so I'm going to come back to the circle. So I'm going to start at s equals 0 and go all the way around to s equal 2 pi r, which is just the circumference. All right. This is actually going to be 2 pi big R. Excuse me. So now we have a fairly complicated thing. When I do this, this whole thing right here will just become 2 pi r, because the integral of ds is 2 pi r. I'm going to let lambda times 2 pi r. What is that going to equal? Remember, lambda is our linear charge density on this ring. If I multiply it times the circumference of the ring, what will that give me? This ring has a charge q on it. It has a radius r and has a linear charge density of lambda, which is the amount of charge per unit length. If I multiply lambda times the circumference, what do I get about the ring? What's that? No, lambda is the density, but if I multiply lambda times the circumference of the circle, of the ring, I get the total charge. So you can think about this in terms of units if you like, that this is coulombs per meter, this is meters, so the meters cancel, and it just gives me the total charge. So I'm going to substitute this and this, just substitute q for that. So E then is zkq over z squared plus r squared to the 3/2. And that's the answer. You can notice that if you let z be much, much bigger than r, that this z becomes a whole lot bigger than r. What does this whole thing reduce to? If this is bigger than r by a whole lot, that means that the r basically just falls out. It's insignificant. It just basically goes to 0 if z begins increasing. And remember what z is. Z is that distance between you and the ring. So as you move farther and farther and farther away from the ring, what does the object begin to look like? What does that expression go to if z is much, much bigger than r? Well, what do you get in the denominator? What do you get? You get a z cubed, right? If I get rid of the r squared, I get z squared to the 3 halves. That's just going to be z cubed. And then I have another z up in the numerator, and so I cancel one of those out. And so I get k cubed over what? Z squared. We already know that. What is that? The electric field of the point charge, right? So a ring, if you have a ring and you're really close to it, the electric field is this value. But as you move farther and farther away, it eventually just looks like a point charge. You should sort of expect that, right? The similar thing with light. You have a ring of light, but then you move it really far away, eventually it's just going to look like a point. Okay? So the electric field just goes to kq over z squared. And this is a point charge. Again, you're not going to see a derivation on the exam. I might ask you 1 or 2 questions in the multiple choice, just sort of about the basis of this, like, you know, like for example, I don't know, I've written the exam, but for example, like this stuff with the vectors, what is your differential element? Nothing too complicated, or maybe something about lambda, or what are your limits of integration, that sort of thing. But you won't see any free response problems. But you will have a derivation that you'll need to do for the exam, and you'll just turn it in at the beginning of class on Friday at 7:15 or 7:30, whenever you choose to come. Should be an easy 10 points. Okay, y'all done this before. If you have questions about what to expect, if you haven't done this with me, then just come see me. I can tell you. Alrighty? I'm not going to do the next derivation. That might be your exam question, or I might give you a sphere. I'm not sure. I might give you a solid sphere. But the charged disk works largely the same. On a distance p, or at a point p, a distance z from the disk, where z is the distance from here to here. There are a couple different ways that you can do this, but the easiest way that you can do it is to let this ring, which you now know the electric field of, let it be your differential element. And then you start in the middle and you integrate outward, but you now have the ring, which we just found, that was the dE equals kz dq over z squared plus r squared. Oh, that should be a little r. Sorry. That is the electric field due to a ring, and that becomes the electric field at this point due to this differential element. And now when you integrate, instead of going around the ring, you're going to integrate from the inside, going all the way out, going from 0 to r, where this becomes your differential element. Okay. It works a little bit differently, but the process is still the same. Tons of good websites that have these derivations. Hyperphysics, I think, has a good one. Just Google, you know, derive the electric field of a charged ring, or whatever it is that I give you. I think also it's in the homework videos as well. Does anybody verify that? Has anybody seen that? If it's in your homework, which I think that is, it's in your, it's in the videos as well. All right, I'll leave that for you, and I'll send you an email out today about your, about the exam. Okay, let's do a few clicker questions. I forget where we left off last time. Chapter 1 still? Somebody tell me where we left off? Things, do you know? Anybody? Tyler, you know where we left off?
1.7, yeah, 1.7.
Okay, thanks, Tyler. This one? All right. Oh, shoot. I'm sorry. Let me pull up my thing. All right, so you're sitting a certain distance from a point charge and you measure an electric field of E naught. If the charge is doubled and your distance from the charge is also doubled, what is the electric field strength now? So go back to our expression for the electric field due to a point charge and then ask yourself, if I double the charge, Q, and I double the distance, R, how does that affect the electric field? All right, we'll do about 10 more seconds, 1:05. I'll put these questions, by the way, on the internet, on the website soon. 1:05, I'll stop. No, that's not right, actually. So, let's see, E is KQ over R squared. I'm doubling the charge. I'm also doubling the distance, so I get a factor of 2 there. So what I get is a 2 over 4. So the actual, oh, it is D. I'm sorry, I thought that was E. Watch out, put E. Nobody put E. Yeah, it is D. It's 1/2. Good job. Between the red and the blue charge here, the red is +1, the blue is +1. Which of them experiences the greater electric field due to the green charge? I'm sorry, the red is +2, the blue is +1. Which of these, this charge or this charge, both of which are equidistant from that green charge, experiences the greater electric field? Think about what the electric field is, and then ask yourself the question, which of these experiences the greater electric field at that point, a distance d from the green charge? Okay, good. A lot of you are getting the right answer. Ask your neighbor if you're not sure. Students are often tricked up by this, so ask your neighbor anyway what they put. Okay, still about half of you don't have the right answer. I'm going to stop at 108. 108. Okay, good. C is the right answer. The electric field, the electric field, if this charge is not here at all, the electric field still remains the same. The electric field due to this charge will remain the same at this point. Right? So it doesn't really matter what charge you have there as to the electric field caused by this charge, it's still going to be the same. As long as this charge is the same, which is the green charges, then the electric field here and here will still be that KQ over R squared. So the electric field is the same for both of these charges, the red and the blue. Which of these experiences the greater force, the red or the blue charge? Or is it the same for both? The electric field is the same for both, but which experiences the greater force? Blue, red, or the same? stop at 45, 45. Okay, good. B is right. The electric field is the same, but remember that F is equal to Q times E. So even though the electric field is the same, the one with the bigger charge will feel the greater force. And you should know that too from Coulomb's law, right? That this Coulomb's law says that the force is Q over R squared. So the one with the bigger charge is going to feel the greater force. Okay? A uniform electric field, an empty space, a 4 Coulomb charge is placed in that electric field, and it feels that force of 12 newtons. What if you put a 6 Coulomb charge at that point? What force will it feel? So I have a 4 Coulomb charge, it feels 12 newtons. What will a 12 Coulomb charge, or excuse me, a 6 Coulomb charge, which is 50% bigger, what force will it feel? Y'all doing awesome. All right, I'll stop at 55, 55. Ask your neighbor if you like. Most of you have the right answer. All right, E is right. 18 newtons. You could do this a couple of different ways. You just look at it and say, well, 4 coulombs, 6 coulombs. 6 is 50% more than 4, so my force is going to be 50% more than 12. 50% more of 12, well, 50% of 12 is 6, so it's going to be 18. Another way that you could do this is you could say, well, this and this, F is equal to QE. So E is F over Q. That's going to be 12 over 4, which is 3 newtons per coulomb. So that is the electric field here. And then if I put in a 6 coulomb charge times 3 newtons per coulomb, then it's going to feel 18 newtons of force. So E is the right answer. What are the signs? Oh, we'll come back to this. All right, let's look at electric field lines. You did pretty well on that. You want to joke? You didn't hit 90%. It's hard for this class to hit 90% because even if you have a couple people that have the wrong answer, because there are so few students, it'll slump down. See, I want to joke? Yeah. Okay, let me think. Oh yeah, so I have this friend. His name is Power. And he's just been really stressed this week because his boss is really mean. He's been making him work overtime. That's the end of the joke. That was good. Y'all get it? Power is work overtime. His boss has been making him work overtime. You tell that one to your friends. They'll love you for it. Okay? Okay, so let's see. We're not going to watch this about Michael Faraday, but you can on your own. There's a really nice, it's really long. It's like an hour, 2 hours long, a PBS special on Einstein. And part of that was about Michael Faraday. Einstein said that Michael Faraday was like the smartest guy in the 19th century. Einstein was the 20th century. Faraday was in the 1800s. And he did a lot of what we know about electric fields and generators and a lot of what we use today to generate electricity. That came from Michael Faraday. He laid the groundwork for a lot of what happened there. So we're going to use electric field lines, which were invented by Michael Faraday, to show the electric field. And the lines are related to the electric field in a couple ways. First of all, the electric field is tangent to the lines. If you're in the lab, you've already done a couple of labs probably on electric field lines. Y'all done the labs where you mapped out the electric field lines on the paper, and then also you did the little simulations. Anyway, the electric field is tangent to the lines. And then also the magnitude of the electric field is given by the density of the field lines. If you're not in the lab, don't worry, I'm going to show you what this means. And this is that PET simulation. I'm not going to do it here, but y'all did it in lab. Or if you haven't, you might want to take a look at it. It'll show you some charge configurations. Or you can make different charge configurations and set up the electric fields for that. I think most of you are in the lab, right? Most of you? Anybody not in the lab? Okay, a few of you are not in the lab. Don't worry, you're not going to be at a disadvantage. But they do go through and model out the electric fields. So if we think about positive and negative charges, these are going to be separate from one another. They're not related. They're not in the same room or whatever. Field lines will emanate outward for a positive charge, like this. But this goes back to what we were thinking about. If I have my positive test charge right here, it feels a force in this direction, and so the electric field is in the same direction as that. They said we're just going to draw a whole array of lines, because if I move this positive test charge anywhere, the force will always be outwards, away from that charge. Similarly, if I have my positive test charge over here, it's going to feel a force in that direction, and so my electric field lines will always go inward for a negative charge. So if I have an isolated charge that's just sitting out in space, this is what the electric field will look like. Remember, the electric field is just a way of mapping out what the force looks like. So it's really describing the physical quantity of the force. It's not something new, it's just something that we use to describe the force. Okay, so at point A, the field lines are more dense than at point B. That is, here, you know, the field lines are just closer together than they are out here. Therefore, the electric field at point A is bigger than at point B. Okay. The density of the lines gives the magnitude of the electric field. And so where the electric field lines are closer together, that means you have a more dense lines, bigger electric field. Where they're further apart, you have a lesser electric field. And we can think about this in terms of force. Here, the force is really big. Here, the force is a lot smaller because I'm further away from that charge. So the force a positive test charge feels at point A is bigger than it feels at point B. Then we can draw some charge configurations. You're not going to have this in your free response, most likely, but you will see some multiple choice questions about charge configurations and just being able to interpret them. So we have some more rules. The lines for groups of charges. Begin on a positive charge and end on a negative charge. If there's an excess of charge, I'll show you what this means. If you have an excess of charge, the line ends at infinity. The line just goes off into space. It never ends. It ends at infinity. I'll show you what that means. If that doesn't make sense to you, it probably doesn't. I'll show you what it means. And then the next thing, the next rule, is the number of lines on a charge that either come out of or go into a charge is proportional to the magnitude of that charge. Is proportional to, remember that symbol? It's a proportionality symbol. Is proportional to the magnitude of that charge. And again, I'll show you what this means. And then this third one is that field lines cannot cross. Which always reminds me, of course, of what? Don't cross the streams. Don't cross. You know the movie I'm talking about? Ghostbusters, yeah. So field lines cannot cross. It literally makes sense if they crossed. Because remember, field lines, this is akin to the net force. The field lines give the direction of the net force that a charged particle feels. So if the field lines cross, what that would be saying that this particle is feeling a net force in this direction and a net force in this direction. But by definition, a net force can only be in one direction. You can't have two field lines that cross showing two net forces in two different directions. All right. I know we just have a few minutes, but let me just show you these. These go quickly. If I have a dipole like this, my electric field, I have electric field lines that come out of the negative, or out of the positive, and go into the negative. I have equal numbers of lines going into or out of each charge. So rule number one was that the field lines come out here, and the field lines go in here. That was rule number one. They come out of positive charges, they go into negative charges. If I have a configuration of charge, there you go, Daniel. I have a configuration of charge that looks like this. We have a plus 3q and a negative q. I have field lines that come over from the positive onto the negative. But then I'm going to have additional field lines that will just go off and end out at infinity. I have a particular number of lines as well. This comes back to rule number two, that the plus 3q charge has 3 times the charge of minus q charge. It has 3 times the charge, and so it has 3 times the field lines. It has had 3 times the charge, and that's why it has 3 times the field lines. So both of those statements are true. It has 3 times the charge and 3 times the number of field lines. All right, I have 6 field lines coming out of 3q. I have 2 field lines going into negative q. If I had 3 field lines going in here, how many field lines would I have to have here? I would have to have 9. I would always have to have 3 times the number of field lines coming out of plus 3q. And here, if I have a plus 3q and a plus q, this is going to look like this. I'll have field lines that come off in this direction, and then over here, in a similar way. See, is that enough? No, I have to have how many?
6.
I have to have 6, right, to represent the disparity between those two charges. They're both positive, so their field lines go away from one another. If they were both negative, if this was negative 3 and this was negative q, the field lines would look exactly the same, except they would be going into the charges instead of out of the charges. Right, I think we'll come back to this clicker question. We have some other questions to do. But that sort of covers all the material for the test. Now on Wednesday, we'll have some time to review if you have questions. Please bring those. But when we run out of questions, I'm going to begin on chapter 0.5. It won't be on the test. We have a few more clicker questions. If you have questions, bring them on Wednesday. We'll go over that. I'll sort of review the test. But then if we have time, we'll move on to 0.5. Have a great day.